Okay, Elena, maybe we can get started now. Yeah. All right, so welcome back. So our next speaker is Jelena from University of Wisconsin-Madison, and she has been doing a lot of fantastic work on variation inequalities and equilibrium. So without further ado, yeah, the stage is yours.
Thank you very much, Neo, and thank you and the other organizers for organizing this great workshop. It's a pleasure to give this talk. So I thought I would talk today about work that I did now more than 2 years ago, but it is still quite relevant. And so I'll spend some time explaining that work, and then I'll talk about some more recent developments, including some work of mine that's not even posted yet. Okay, so I'll start with the basic motivation, which comes from min-max optimization, and I will not be spending too much time here because I feel like you have seen this over and over again, so no need to dwell too much on it. But the basic motivation for what I'll be talking about is min-max or saddle point optimization, where we want to minimize a function over x and maximize over y. I will always be assuming that if we have a constrained setup, that these feasible sets x and y are closed and convex. And for most of the talk, I will be assuming that this function f is convex concave. And then towards the end of the talk, I will mention some extension to cases when the function is potentially not convex concave. One of the most basic facts, as we all know, is that when we have a function that is convex concave and the feasible sets that are compact, then min-max point is guaranteed to exist, and the min and max are exchangeable. There are, of course, some generalizations to this seminal result of von Neumann, but in general, once we relax the condition that the function is convex concave, we cannot go much further in guaranteeing a result like this. The problem becomes, in fact, very difficult, as you have seen also in other talks that mention some of the hardness results. There is a whole research area that looks at when local solutions even exist, and there are different ways of even defining what local solutions are, as we saw in Lipschitz talk. But we do care about these setups where the function is potentially non-convex, non-concave. When it comes to the types of guarantees that we typically look at when we have some candidate approximate solution, there are two most basic guarantees. The first one is guaranteeing that we have a small optimality gap, or maybe more precise thing to say here would be a primal dual gap. So what we want to ensure that when we move away from our candidate solution in either y direction or x direction, we cannot improve by more than epsilon. This type of guarantee is mainly meaningful for convex concave functions. There is also another guarantee that we can talk about, and it is stationarity guarantee. It is meaningful in any setups where f is also potentially non-convex, non-concave. I will mainly talk about setups where f is differentiable, so I can write things like gradient. This is just a generalization of stationarity you would have in standard min optimization, and if the setup is unconstrained, it just reduces to requiring that we have a small gradient. Now, I'm giving here min-max optimization as the main motivation, but there are much more general problems that can be studied, and the work I'll talk about actually covers also those generalizations. So in terms of the basic problems that we tend to look at as abstractions of min-max, but also generalizations of min-max, we often work with operators that are monotone. And the monotone means that we can satisfy an inequality that looks like this. Now, gradients of convex functions are monotone, but also for convex concave functions, if we take the if we stack the gradients and we put a minus here with respect to the concave part, we also get a monotone operator. If a function was not convex concave, then we wouldn't have a monotone operator. There are some basic variational inequalities problems that are usually defined for monotone operators. And they are defined in terms of what looks like equilibria. So we want to find the solution point U star such that we satisfy some type of an inequality. And there are two types of inequalities. They correspond to weak and strong solutions. The difference here is where you evaluate this operator F. If this doesn't make sense, don't worry about it. I will give you kind of the bottom line of the story very soon. There is a third type of a problem, and then that's the one I have been focusing on, which is known as monotone inclusion, where we want to find a zero of this operator F. Now, this is just finding a zero of F is sufficient for unconstrained setups. There is another part we add here when we also want to cover constrained setups. So this would just be the subdifferential of the indicator function of the convex set. Mainly what it does, it just ensures that the problem is still meaningful and gives you the right notion of stationarity if a solution happens to fall on the boundary of a feasible region. If you want an intuitive way of thinking about these problems and translating them back to min-max optimization, variational inequalities will normally translate into guarantees on optimality gap, or more broadly, primal dual gap. Monotone inclusion will be translating into the problem of finding a stationary point. So in unconstrained setups, finding a point with a small gradient. Now, if you want to compare these three types of problems and their corresponding solutions, there's a very basic fact that says when we have a monotone operator, then the solution sets of all these three problems are the same. So there is no difference in whether you're solving monotone inclusion or either one of these two variational inequality problems. So, you might be already wondering, so why am I focusing on monotone inclusion? Well, the thing is, we never really solve these problems to optimality. What we can only hope for is that we solve them approximately. So when we are solving these problems, we would be solving them to some accuracy epsilon. Now you can define the appropriate epsilon approximations to these problems. For monotone inclusion, you just add some epsilon margin. This is a ball of radius epsilon, and it means exactly that. So if you were looking for a small gradient, it would mean that you find a gradient with norm at most epsilon. And you can define the same thing for variational inequalities, where you replace this zero that was on the right-hand side by some epsilon. Now, the things become much more interesting when you look at approximate solutions, because already when you start looking at the unconstrained setup, approximations to weak and strong VI solutions become meaningless. And what I mean by that is that unless you have an optimal solution, the guarantee that you get would be that you have an infinite error. And let's quickly look at just a very simple example. So consider having a bilinear problem, and just x times y. The monotone operator you get from there would be y and minus x, just according to the definition we wrote before. And this problem actually has a solution, and it is unique at 0, 0. Now, if you try moving away from 0, 0 to any other point, and you look at the guarantees you can have, well, this here would be your strong solution guarantee. You need to take supremum because this inequality needs to hold for every U from a feasible set. And now feasible set is all of R2. By monotonicity of this operator, this is greater than or equal to the weak solution guarantee. Now you plug in the definition of F in here, and you get something that looks like this. Now it should be immediate to you because I'm taking supremum over x and y. If I have x bar and y bar, where either of them is non-zero, I can push the supremum to infinity. So what this means, I'm giving you an example that if you're in the unconstrained domain and you want to have the direct definition of what approximation is for variational inequalities, and in this case also for the optimality cap, then this it does not make any sense. Now, there is more to say, even in cases when you have constrained setups that are bounded. So the diameter of the set is bounded. And what you can say in general is that the set of all of epsilon approximate VI solutions contains all of the epsilon approximate strong VI solutions, which in turn contains all the epsilon over D approximate solutions to monotone inclusion. What this means is that if I solve monotone inclusion to error epsilon over D, I get an epsilon approximate solution to strong VI, and I also get epsilon approximate solution to weak VI. So monotone inclusion is in fact the most general of these problems. And this epsilon over D actually doesn't lose anything. So if I have an algorithm with optimal iteration complexity for monotone inclusion, it immediately implies algorithms with optimal iteration complexity for either of the two VI guarantees. This is the reason why I was interested in monotone inclusion. Now, the work I did was back in 2020. So this will mainly summarize kind of history bits up to that point before this work existed. And I'll talk about some developments that happened after that in the later part of the talk. So as far as I know and could find just by searching the history of these problems, min-max optimization was originally studied within game theory and economics. And at least initially, people were mostly concerned with the existence of equilibria, with the existence of min-max solutions. Variational inequalities, even though they are today studied as abstractions of min-max, actually came from a different line of work. They started with something called Signorini problem in 1959, which is an equilibrium problem that comes from dynamical systems. And their systematic study started in 1960s. It was initiated by Guido Stampacchia, after whom strong VIs are named. And he was the person who coined the term variational inequalities. Now, in terms of algorithms, these connections between variational inequalities and min-max optimization were observed quite early on, and many of the algorithms that were developed would apply to both problems. In terms of the asymptotic convergence, we have results at least as early as the 1970s. In terms of non-asymptotic convergence, where we have explicit rate guarantees, the first type of results that existed were for the setups where you can obtain linear convergence. And so these applied to, at least in the setup of min-max optimization, to problems that were either bilinear or strongly monotone. Now, when it comes to convergence to weak VI solutions, and you look at standard classes of problems, so you don't necessarily require that you have this strong monotonicity. So you have things like bounded gradients, Lipschitz gradients, and so on. There was a lot of work, starting at least with the work of Nemirovsky, and there has been a lot of follow-up work more recently in the ML community that gives different interpretations of these results and maybe some nicer proofs. But here, in the case when we have Lipschitz monotone operators, we can get complexity that is of the order 1 over epsilon. And if you move away from weak solutions, So if you want guarantees for strong solutions or monotone inclusion, there was much less work, at least when it comes to having rate guarantees. Prior to my work, the main two results I'm aware of were the results of Dan Ganlan and Ru et al. The bounds they got were suboptimal, and I'll show them in a table in a bit. Okay, so the results I will be talking about here are from this paper that appeared back in COLT 2020. I apologize for the noise. There is a train going next to my office, and that's what's causing this noise. Hopefully you can still hear me. So to make stating results a bit easier, I will just focus on the basic version of the results, but you can state them in full generality for monotone inclusion. I just want to give you kind of an easy picture to keep in mind. So the most basic goal is that we have a convex concave function. So this F operator that I'll remind you what it is here in the corner is monotone. And we are given an error parameter epsilon, and we want to find the point that has the norm of this operator that is at most epsilon. Now, this problem, as I said, is well defined even when approximating the gap is not. And in general, what can be said is that if I get an optimal rate for making this operator norm small, it implies the optimal rate for the optimality gap. Now, you may be wondering whether the opposite holds as well. And as you may suspect, it does not. And it is not only, artificial that it does not hold in general, but if we look at standard algorithms that we would use for the optimality gap, for those algorithms, we would provably get suboptimal rate. So what I can tell you informally is that if you have a Lipschitz monotone operator, the optimal rate for reducing this norm of the operator is 1 over k. If you look at the algorithms that achieve that optimal rate for reducing optimality gap, so things that you're all familiar with, like extra gradient, mirror prox, Popov's method, dual extrapolation, all of these methods and methods similar to them have suboptimal rate for reducing this norm of the operator, and it is not faster than 1 over root k. And this follows from the result of Golovic, Patatil, Daskalakis, and Ozdaglar from COLT 2020. Now, to state the results, I need to tell you what are the problem classes I look at. And the problem classes I had looked at are all the standard problem classes where you would have Lipschitz monotone operators. So the first problem class corresponds to operators that are cocoercive. This is a very, very strong assumption. It implies that the operator is both Lipschitz and monotone. The opposite direction does not hold, but it is the most basic case to understand. And as I'll show you, when you understand this basic case, it is possible to build on it and obtain results for other problem classes. The other problem class is when F would be monotone and L Lipschitz, and it's your standard definition of Lipschitzness. The third problem class would be when F is, in addition to being L Lipschitz, also M coercive or M strongly monotone, meaning that there is this quadratic lower bound on this inner product. So just to quickly compare these two things. So this would correspond to things like to a function being strongly convex, strongly concave. If you had a 0 here, it would just mean that the operator is monotone. When you have this quadratic distance, it is strongly monotone, and this is the strongest assumption that you can make here. cocoercive is different because here you have f of u minus f of v instead of u minus v. I should mention that the results I'll present, in fact, apply to a relaxed version of strong monotonicity called sharpness, where an inequality like this would apply when you restrict one of the points to be a solution to the problem. So there are problems that are sharp, but they're not strongly monotone. It is a wider class, but to be able to compare to other results and not to complicate things too much, I will mainly be mentioning strongly monotone, but I just wanted to mention this to you in case you were wondering. Now, my focus in this first work was mainly on methods that are parameter-free, meaning that they can work without knowing what these parameters L and M are. So the method can know what problem class the problem comes from, but not know either of these parameters. Here is a big table that summarizes the results, and it's a bit too much, so I'll tell you how to read it. So there are three main columns, and these three main columns correspond to the three classes of problems. So cocoercive, Lipschitz and monotone, Lipschitz and strongly monotone. And then there are three sub-columns for the three types of solution: weak VI, strong VI, monotone inclusion. The first row are the results from my work. The second row are the best known results at the time this work was done. And the green color here indicates that the results are parameter-free. You do not need to know parameters, whereas red here means that you do need to know the parameters for those algorithms. And so for the cocoercive class, we already had a good sense of complexity. And there were methods out there that were getting the optimal iteration or oracle complexity. But we didn't have parameter-free algorithms for stronger guarantees. For Lipschitz and monotone, it is not only about the complexity result. So here, this O tilde just hides log 1 over epsilon factor. So it is slightly worse for weak VI. But for the other two cases, at the time this work was done, there was a quadratic improvement here in terms of the dependence on epsilon, the diameter of the set, and initial distance to the optimum. For the Lipschitz and strongly monotone results, the parameter-free part is a little bit implicit in one of the papers here, but I have checked and it works. It is possible to make those algorithms parameter-free. The result I get here is off by a factor log condition number, so log L over M. But it applies also beyond strong monotonicity, as I said, to this sharpness setups. So let me now tell you a little bit about how these results were obtained. And all of the results I'll talk about are one way or another related to something called Halpern iteration. So what is Halpern iteration? It's a very, very old algorithm. It was developed in 1967. And traditionally, it was used for solving fixed point equations of non-expansive maps. So non-expansive map means that you have a map that is one Lipschitz. It doesn't expand distances, but it is not necessarily contractive. Fixed point, I hope you know what fixed point means. So there were results that were established in non-asymptotic rates for Halpern. Most of them were not that great, but then sometimes 2017, there were two papers that got this rate, which is of the order 1 over k. I'll mention maybe this briefly, but this also turns out to be the optimal rate you can get. So, this is for non-expansive maps. What's the point? I'm not looking at non-expansive maps. Well, non-expansive maps are very closely related to cocoercive operators. in fact, that there is just a linear transformation that would take me from one to the other. So if I have an operator that is 1 over L cocoercive, I can just take identity minus 2 over L times F, and I'm going to get an operator that is non-expansive. So in principle, I could be applying Halpern iteration to this non-expansive operator. Now, the question is why, and does this give me anything? Well, if you actually take this transformation and you look at what is the fixed point now of this non-expansive map that I defined, well, you write the fixed point, and this essentially means just that you're finding the zero of this operator, and that's what we want. So this precisely gives me what I want. And in terms of these existing results, if you just do the translation, they would already give you 1 over k convergence rate for making this operator norm small, but you would need to know this parameter L to be able to apply it. So what I was wondering about when I started working on this problem was, can we do this without knowing L? And also the analysis that was presented in a leader's paper wasn't quite clear what was going on there. So I wanted to develop a different convergence argument that I could build on. So from now on, the algorithm that we will work with is just this equivalent variant of Halpern iteration, but now applied to cocoercive operators. And yeah, maybe let me just quickly note. So what is interesting about this algorithm, that it does something called anchoring. It always mixes in a small amount of the initial point. And then this other thing you can think of as a gradient step. Seems like a minor point, super important for convergence. If you remove this, you probably would not get the optimal rate. So it is this anchoring is super crucial. This step, lambda k, is usually of the order 1 over k. Okay. So the analysis of the algorithm that I came up with back in this work was based on a potential function. And this potential function and the algorithm will use some guess for the cocoercivity parameter. And as I said, this lambda k is just the step size. There is intuition behind this potential function in that it does a kind of a trade-off between the norm of the operator and some notion of a gap with respect to the anchor point. I won't get to talk about it here. I have other works that actually show that for other algorithms in other setups that are that give optimal guarantees in terms of the gradient, you can usually come up with potential functions that look like this. So there is kind of a broader phenomenon of what is going on here. Now, why is this potential function useful? Well, the analysis hinges on the following argument. So you want to argue that this potential function is non-positive for all k. And then if you have something like this, you just rearrange this thing being less than or equal to 0, and it gives you a bound on the operator norm squared. And now the question is, how to use this? Well, it's actually quite simple. You add and subtract some solution, U star. Because it is a solution, you can argue that this part will be non-positive. And you apply Cauchy-Schwarz to the first term, and you get something like this. If the operator norm was 0, you would have already been done. So assume it is not. You cancel it on both sides. Sorry, my slides are not updating well. So you cancel it on both sides, and you get something like this. So it gives you a bound on the operator norm at iteration k in terms of the initial distance. Now all that remains is to ensure that this works for your estimate being correct, not being too much off by more than a constant, and that can be guaranteed, and that the analysis works for step sizes of the order 1/k, and that's what is done in this paper, and you get the correct iteration complexity. Now, this is the most basic setup, and it is possible to extend this result to other problem classes. Because I won't have enough time, I will not be telling you, I will not be giving you all the details on how to do that, but let me just hash out the main ideas for what you would do. So what I talked about was for unconstrained setup. You can also generalize to constrained setups using something known as operator mapping or natural mapping. It is similar to gradient mapping in convex optimization, and it is kind of the, it seems like the right thing to do when you have projections. To go to setups with monotone and Lipschitz operators, there is a way to do that by using something called a resolvent operator. There is a standard fact about resolvent operators that when you have an operator that is monotone and you apply a resolvent to it, you'll get a non-expansive operator. Now, because you get a non-expansive operator, you can apply this, you can apply Halpern iteration to it. There is, of course, some technical work missing there because you need to get an algorithm that computationally makes sense, you need to work with inexact resolvents. So the analysis needs to be extended to work with inexact operator evaluations. And this is what is done. What you lose in the process is just this log1/epsilon factor. So it becomes kind of a two-loop algorithm. And to go to strongly monotone setups, what is shown here is that you can use adaptive restart. Mainly, you use this algorithm for monotone Lipschitz case, and you just restart it every time you half the operator norm. And all of these results are near optimal. So in this work, we actually certify that using lower bound reductions from a result that holds for optimality gap in min-max optimization and was obtained by Wu, Yang, and Su. So this essentially resolves the whole class up to some logarithmic factor. What I have not explicitly mentioned here, but it should be clear to you from this guarantee, is that all of these results are for the last iterate. There is a particular reason I really, really like Halpern iteration. Well, there's more than one reason, but one of them is this very interesting structural result that tells us that Halpern iteration is implicitly regularized method. And what I mean by that is that if you have a problem where your solution is not unique, then Halpern iteration is guaranteed to converge to the closest solution to the one from where you started. So if you have 0 within your feasible set and you initialize from 0, you get a minimum norm solution. Now, the results I have talked about so far, although I didn't explicitly say this, they're all for Euclidean norm. This structural result holds for any norm. In particular, holds even if you have L1 norm here. So if you could make this work for L1 norm, you would be getting implicitly sparse solutions. Now, what I talked about were the results from the work back in 2020, and now I want to tell you about some more recent developments and what has been improved and tightened since the initial dissemination of this work. There were improvements to lower bounds. So because the lower bounds in my first paper were using these lower bound reductions, they were not tight, they were losing some log factors. So I had a paper about a year ago with my student that showed that for the cocoercive setup, this type of lower bound holds. So this direct application of Halpern iteration to cocoercive setup is optimal, gives you iteration complexity optimal result, or oracle complexity optimal result. Cocoercive implies a lower bound also for monotone and Lipschitz. I should say, however, the lower bound we had here, it had some restriction. It wasn't just the first order oracle lower bound. We were assuming, that the new point you construct based on previously seen operators or gradients. There is a strengthening of that result to just gradient oracle setup by Yoon and Ryu, and it calls for monotone Lipschitz operators. What you can conclude from here is that the result I told you about that uses resolvent is just optimal by log 1 over epsilon factor. There have also been improvements in terms of the upper bounds. So the same paper by Yoon and Ryu actually shaves off this log 1 over epsilon factor. Instead of having this inner loop, they get an algorithm that is similar to extra gradient, but it is not extra gradient. It is a variant of Halpern iteration. It's just a two-step variant of Halpern iteration. And based on this lower bound, this is optimal iteration complexity. And there was another paper that also appeared in 2021 that gets the same result, but for an optimistic or Popov-like variant of Halpern iteration. The difference is just that here you would need 2 operator evaluations per iteration. Here you need only 1. And this paper also gives some other results. One thing that is very interesting to me, and this is to my current understanding, there may be something I'm missing, but you can correct me if I'm wrong. So far, the results of this type that give you guarantee for the last iterate and give you oracle complexity optimal results are all based on Halpern iteration. So it seems to be kind of the correct view of the problem, this view of relating cocoercivity with fixed points of non-expansive maps. And when I say last iterate, I mean that you get the optimal rate for any notion of convergence only with the variant of Halpern iteration. And in fact, Halpern iteration gives you the strongest guarantee you can get, which is the guarantee for monotone inclusion. There have also been extensions that go beyond monotone setups. And one such extension is to something, to a setup where you have a property called negative comonotonicity. This is a typo here. It should be f of u minus f of v. Sorry about that. So the negative comonotone gives a condition like this. It just should be f of u minus f of v again. Now, this negative comonotonicity has been studied since at least the 90s. It came up in works that were trying to understand why some variants of proximal point method were converging even on problems that were not monotone. There have been multiple characterizations of what it means to have negative comonotone operators. One of them is that the resolvent operator is non-expansive. This is a resolvent operator. Now, what this means is that the results from my paper from 2020 already implies that if you apply Halpern iteration with resolvents, you get something close to the optimum for rho less than 1. So you lose log 1 over epsilon here for approximating the resolvent. The reason I did not include this back then was that the algorithm was not parameter free and it kind of didn't fit nicely with the whole story. There are improvements to this result. And there was a paper by Lee and Kim that gets a result without this log 1 over epsilon where you just restrict this row to be up to 1 over 2L. Whether this is necessary or not, we don't know, but it is a very, very nice result and quite technical to get. It is based on an extra gradient like variant of Halpern iteration, and their result can be made parameter free. It's very nice. Beyond Halpern and kind of in the similar class of problems, we had a result that was addressing a broader class than this co-monotone, where you only need the property like this to hold when one of the point is optimal solution. But the complexity becomes worse. So it goes from 1 over epsilon to 1 over epsilon squared. Okay. The final thing I want to talk about, and then I'll wrap up, I just need a few more minutes, is when we have stochastic setups. And this is a very, very recent work with my student Shufan Tsai, my postdoc Xiaobing Song, and my collaborator Cristobal Guzman. The paper is not online yet, but we hope to post it very soon, maybe the next few days. So we look at this problem of monotone inclusion. So the same setup, same classes of problems, but now we assume that we have stochastic oracle access to this operator. And there are standard assumptions you can always make in stochastic approximation settings, that you have an unbiased estimator and bounded variance. There is an additional assumption that we make, which is this multi-point oracle assumption made also in some prior work, which just assumes that you can query multiple points with the same random seed. We don't know how to get the results I'll talk about without this assumption. Seems kind of crucial. If you can relax it, that would be very interesting. If you look at the prior state of the art, the best results for stochastic setup that I'm aware of are of the order 1 over epsilon to the 4th. And there are a few papers that can get this type of guarantee. They would typically use mini batching. And they do not actually need this multi-point oracle assumption. But what this buys us is that we can do variance reduction. I'll talk about that in the next slide. There are better results than this. So this seems rather high. There are better results for optimality gap, classical ones, also some more recent ones. It's unclear how to translate them to the gradients or this monotone inclusion. So our basic idea in the work was just combine all these optimal variants of Halpern iteration, which we know are iteration complexity optimal in the deterministic setting, combine them with variance reduction. And there was a question what variance reduction method to use. There is a specific recursive variance reduction method that worked well for us. It's called Page. I suspect that others would work too, but this one was just convenient for the analysis. That method was developed originally for non-convex optimization, where you're just minimizing the function. As far as I know, it has never been used in this specific setup. Idea is super simple. We knew exactly what we wanted to get. Getting there was quite complicated, and we end up with a pretty intricate inductive argument, even though we used the same potential function as before. So these are the results. So without variance reduction, the complexity was 1 over epsilon to the 4th. Here we reduce it to 1 over epsilon cubed. And then for the Lipschitz strongly monotone setup, we get 1 over epsilon squared log 1 over epsilon. Now you may be wondering, can you do better? You can't. So it is possible to argue that this is optimal up to log factors. I'm displaying the dependence here only on epsilon. There is dependence on other parameters. That dependence, I think, can be improved, but the dependence on epsilon, no. Okay, so there are two main things I want to tell you here. For all these standard classes of problems with Lipschitz monotone operators, we get iteration complexity optimal results with variance of Halpern iteration. as far as I know, only variants of Halpern iteration give this type of results. So I believe this is worth further study. Another thing that I find interesting is that all the existing arguments for these variants of Halpern iteration are based on the same potential function, which was introduced in this work from 2020. And there is a downside, and that is that all of these results are only for Euclidean norms. And we also care about other norms. So some open questions. First is, can we generalize this to other norms? And in particular, I would be very interested in L1 norm. There are reasons why this is difficult. I don't have the time to get into that. Are there other types of algorithms that can give these results and that do not boil down to some variant of Halpern iteration? I think it's interesting to understand. And can we address more general non-monotone setups and still get these same nice optimal rates? So I'll stop here, and I'm happy to take any questions you might have.
All right, thanks a lot, Jelena, for the very nice talk. Yeah, let's see if there are questions here.
Mm-hmm.
Hello, Jelena. Thank you very much for the talk. I would like to ask a question. If you have some intuition, why in the stochastic case you get the, if you go 2 slides before that one,
Yep.
Yeah, that one. Do we have, I will focus in the L Lipschitz and M strongly monotone case, that it is like the bread and butter in the literature. Why we get the 1 over epsilon squared in comparison with 1 over epsilon? Is it a very clear reason that we have to get to 1 extra 1 over epsilon in the stochastic case? Thank you very much for the.
Yeah, so thank you. That's an excellent question, and fortunately not too hard to explain. Are you familiar that in the setting with min-max, actually even in convex optimization, if you have smooth strongly convex function, for the optimality gap, the complexity is 1 over epsilon? Okay. Can we agree on that?
Yeah.
Okay, so the optimality gap is bounded by a norm of the gradient squared. Okay. So to translate from 1 over epsilon to 1 over epsilon squared, that's exactly where the complexity comes from. You would need, so it's just a direct reduction, because you would need to make the gradient of the order 1 over square root epsilon.
Oh,
if you have,
I got
you got it? Okay.
Thank you very much.
Yeah, and then to get to this one, it's actually just based on our algorithm. So we go from here to here using restarts. So what we argue is if you had anything better than this, you would improve this bound, and then you contradict the lower bound for Lipschitz strongly monotone.
I see.
Yeah, thank you. That's an excellent question.
Okay, so there's another question.
Hi, Jelena. This is Yu Jia. Thank you for the very nice talk. I just have a few questions on, so if we are considering L1 norm, do you think the definition of the gradient being small still makes sense? Because, for example, if you're thinking of a constrained bilinear game where the domain setup is L1, then I worry that if we have a strong duality gap guarantee, that would not necessarily mean that the gradient in any norm would necessarily be small. So this is my question.
I'm not sure I fully follow the question. So, and then this is just basically my misunderstanding. So for the L1 setting, we would want to bound the gradient in the L infinity norm.
I agree.
So we always use the dual norm for the gradients.
I agree that like the gradient norm being small would be a stronger like it would imply that the strong duality gap or the weak duality gap. My question is, do you think there are possibilities that the there are solutions that satisfy strong or weak duality gap, but there is no point that has small gradient?
Okay, I do not. So the general correspondence between the problem classes I talked about, it holds for any norms. So if you can get a guarantee for the optimality gap, for any of these notions of gaps, it would be implied by the small norm of the gradient or of the operator. And in terms of the existence of optimal solutions, if one exists, all of them exist. So this is kind of the notion of norm is irrelevant here because of the equivalence of norms in finite dimensions. The reason why we don't directly translate from one norm to another is that you would lose factors polynomial in D. Does that make sense?
Yeah, that makes sense. I guess another way to say, an easier way to say my question is that if we consider a constrained domain in a Euclidean space where there is no solution, so it's away from the 0 point, so there is possibly no solution that the gradient can be possibly small. If you just
I see. In the constrained domains, you wouldn't want to make the gradient small. You need a different notion of stationarity. I just used the small gradient because it was simple to describe because of the it's a simple to describe notion of stationarity. If you go to constrained domains, you need a different definition of stationarity. You need this kind of local improvement. Because you need to account for the possibility of the solution ending up at the boundary of the region.
So all the results also extend to the constraint case, you're saying?
The results from my 2020 paper extend to constraint setups where you have projections.
Okay.
Some of the follow-up results do not extend to constraint setups yet. But I think should be possible to extend.
Okay, cool. Yeah, thank you. And another question I have is, would you mind going back to the contribution of your first paper page, the comparison between the rate and the state of the art? I was wondering.
Yeah, I'm probably missing something, so I'm happy to add more.
No, I have a very basic question. If there are L over M rates in the literature for L Lipschitz and M strongly monotone, why wouldn't that correspond to L over epsilon rate in the L Lipschitz and monotone case?
Oh, that's a very good question. So this result here was proved for the extra gradient. Yeah, and it would make sense that it translates into L over epsilon. So you can, if you use just some type of regularization, I guess you can also get this result by losing log 1 over epsilon, but you would need to know a bunch of parameters, like you would need an estimate of distance to opt.
So you're saying the point of the algorithm methods you list here is because they are parameter free.
Yeah.
Got it.
Yeah, so you don't need any estimate of distance to opt or L or anything else. But yeah, that's actually a very good point. Yeah, thank you.
Got it. Okay, cool. Yeah, thank you.
No problem.
Let's thank Elena. Okay, I do want people to have their break. So
yeah,
I have a couple questions. I will just ask you offline after this is over. Yeah, thank you very much. Yeah.
Okay, sounds great. Thank you all. See you all. Bye.